Hello again, and I am back, and today we're talking about curve analysis part 2. Now, in the last video, we started looking at the beginning of curve analysis, in which what we talked about, recall that f prime of x, if the derivative is positive, then that implies that f of x is increasing. Its function before is increasing. And if the slope function, if the derivative is negative, that's if and only true if f of x is decreasing. And again, think about anytime you see derivative on a graphically, remember that the derivative is all the instant rate of changes. It's the slopes of the tangent lines. Emphasis on the word slopes. All right. So that's where we're coming from. And now this video right now, I'm going to cover a lot of definitions of a lot more things that are happening, and we'll look at an example of it in this lesson, and you'll see more of it to come in the future lessons. Right? So really what I'm going to do is I'm going to cover the math notes in 332 and go into a little bit more depth of what each of those words means. Right? And we're going to do it through an example. So let's say we're given f of x, and I'm going to do a graph off to the side here. And I'm going to draw in a certain way that allows us to get some key points from this. I have it go up here to bounce off and come up. All right. So let's say we have f of x that looks like that given graph that I drew there. Now, what we know from the last video is that we can say that f of x is increasing from, now we're looking at, if we're talking about f of x is increasing, remember we're looking at the slope, and when is the slope positive? Well, the slope is positive from -1 up to 2. So we could say from -1 to 2, the slopes are all positive here. And then it becomes negative, and then it's positive after 2 to infinity. The slopes are all positive, so the union of 2 to infinity. And we could say since f prime of x is positive. Okay. Similarly, we could say f of x is decreasing from -infinity down to -1 with the intersection of 2, or why is that 2? That should be a 1 to 2. Let me fix this up here, miscounted. -1 to 1, it's increasing, and from, that's okay, from 2 to infinity, that's okay. So it's f of x is decreasing from -infinity to -1, and it's also decreasing from 1 to 2, since f prime of x is less than 0, it's negative, right? So that's covering the keywords increasing and decreasing, okay? And focusing on using the definition of its derivative. Now, we're going to talk about the critical points here, and what I'm going to do here is I'm going to make a number line of f prime of x. And what I want to do on this number line is locate its zeros. When is the slope 0? So notice the slope is negative up until at -1. At -1, the slope becomes 0. So at -1, there's a 0 there, so I always put a 0 above it. And then the slope is positive, and then at 1, the slope is 0 again. At 1, we have a 0, and then the slope is negative, and at 2, the slope becomes 0 again. These right here, the -1, the 1, and the 2, these are called critical points, since f prime of x is equal to 0 at those points. So that's a new word, and that's not in the math notes. I don't know why they left it out, but I'm throwing that in there. Push this to the top. Okay. Now, one thing I like to do on these number lines is when we look at f prime of x is I want to analyze what's happening to f prime of x in each of these intervals. Imagine drawing like a vertical line, and I just created, because of these zeros, there's 1, 2, 3, 4 different intervals. Now, before -1, f prime of x is negative, so put a negative there. Between -1 and 0, f prime of x is positive. And usually it won't get as messy as this because I'm not circling and drawing dashed lines. I'm just doing negatives and positives. Between 0 and 1, oh, I'm sorry. It's positive between this whole interval, -1 to 1. See, I already got lost. 0 was not a critical point. Between 1 and 2, the slope is negative, and after 2, the slope is positive. Now, these critical points matter because they tell us possible extrema, which are maximums and minimums. And there's actually two types. There's local, there's local and global. We're only covering local this chapter for now, but just letting you know it exists. So what's happening here is at -1, it's changing from negative to positive. So at x equals -1, f of x, we could say, has a local minimum since f prime of x changes from negative to positive. And that's shorthand. It's not necessarily the best way to write it, but at this point, I want you to understand the concept. Right? So anytime f prime of x, anytime a critical point changes from negative to positive, that means that f of x at a local minimum. You can see on the graph at -1, it's at a minimum. Slopes are changing from negative to positive. Right? It also, at x equals 1, we look at our next critical point, it's changing from positive to negative. And if you look at f of x, when it changes from positive to negative, that creates a local maximum. Since f prime of x changes from positive to negative. Right? And at x equals 2, at x equals 2, f of x is going from negative to positive again. And when f prime of x goes from negative to positive, we know that that's a local minimum, just like at -1. You can see it's going from negative to positive in our number line up there. So f of x has a local minimum again, since f prime of x changes from negative to positive. So that's a new word for us. So critical points tell us possible extrema. In these cases, we have a local minimum, a local maximum, and another local minimum. Now remember, I said another one's global, where you can picture what's the difference between local and global. And why were these locals? Might be something to think about when we get to that definition. Okay. Now the new word we're going to talk about, and there's something new, is now we're going to learn something called concavity. And concavity deals with the rate of change of the rate of change. So that's dealing with f double prime of x, or the second derivative of f of x. So now let's graph f of x. Let's graph the derivative f prime of x. Okay. This will help us with the concavity and make some connections. So what we know here, the critical points, is f prime of x has zeros at -1, 1, and 2. So at -1 there's a 0, at 1 there's a 0, and at 2 there's a 0. And if we follow this, before -1 it's negative, and it goes from negative to positive, so we'll be doing something like that. At 1, it's going from positive to negative, and at 2, it's going from negative to positive again. So this graph if we do a sketch, it looks something like this. Just a sketch. It gives us an idea. Okay. Now, what's concavity is similar to like a minimum and maximum when f prime of x is changing from negative to positive or positive to negative. Concavity is when f double prime of x changes sign. And that's what concavity is. So there's two situations you can have. Is you can be function f of x, we call, is concave up if f double prime of x is positive, and f of x is concave down if f double prime of x is negative. Push my paper up. Now, if we look at this graph f prime of x and we were determining concavity, we'll notice that now we're looking at the slope of f prime of x, because f double prime of x is the slope of its previous function f prime of x. Right, so again, f double prime of x, note, do it over here, note, f double prime of x is the slope of f prime of x. Right. So when is this function concave up? So this function is concave up from negative infinity up until 0. So if we mark that as 0, so this function is concave up from negative infinity to 0 because the slopes are all positive. And then it's also positive from, that looks like 1.5 to infinity. And when is this function concave down? And you can put since f double prime of x is positive. The slope is positive there. And concave down, it's concave down from 0 to 3/2. Since f double prime of x is negative there. The slope is negative on the interval. Now, if we relate back to f of x, what does concavity mean on f of x? So we can see what concavity means on f prime of x, it's the slope, but concavity on f of x, right, if it's concave up, the graph, you're talking the rate of change is increasing. The way the rate of change is changing is increasing. And what that looks like on a graph is it kind of looks like anything that has a bowl like it's holding water. Right? Similar. Concave down is it would be like it's losing water. Right? A curve would be losing water. You can see it up and down. Right? Now, if we look at f of x in this function, let's see. So we said it's concave up from negative infinity to 0. So from negative infinity to 0, it's concave up. So this whole interval right here that I'm highlighting in red, it's concave up. And you can see how the idea is that f of x is holding water. And it's also from 3/2 to infinity. So 3/2, notice that's in the middle right here. It doesn't. So that's the one tricky part of concavity is it doesn't necessarily go up to the next highest point. So there it's concave up. And then it's concave down from 0 to 3/2. So from 0 to 3/2, this area right here, notice how it'd be like losing water if it was like this upside down bowl, and that is concave down. So concavity is talking about the function f of x, but you use the second derivative to talk about it. Now, Does this function have concavity? Yeah, it does, because f prime of x changes sign, and it has concavity at 0 and at 3/2. And at 0 and 3/2, it has concavity. And then remember, it kind of, make sure you understand that concavity, with it comes concave up and concave down, in which we looked at concave up as if the second derivative is 0, in which we used f prime of x to determine that, and concave down if the second derivative, the rate of the rate change is negative, which we used f prime of x to help us with that as well. Right. Now, before I end this video, let me quickly look at the math notes and make sure that covered everything. All right. So if we look at these math notes, we talk about increasing, decreasing. It did mention dy dx. So dy dx is just another way of saying f prime of x, the changes of y with respect to the changes of x. So it's talking about those finite differences. Extrema we talked about, and critical points. The slopes of the tangent lines when they increase. So when the second derivative is increasing, when it's positive, the graph is concave up, which we talked about. And when the slope decreases on the wheel, so when the slope of the slope, in other words, the second derivative is decreasing, when it's negative, it's concave down. Right? That's what I wanted to say. I made one mistake, and that's the last keyword. So let's go to my video. This word right here, it's not concavity. These two are concavity. And hopefully you're still watching my video and you didn't cut it short, because then you'd have some mistakes. I forgot one more word. When f double prime of x changes sign, that is a point of inflection. So a point of inflection is when the second derivative changes sign. In our case here, where were the points of inflection? They were at x equals, well, the second derivative changed sign at 0 because it went from positive to negative. And then also, the f double prime of x changed from negative to positive at 3/2. So when it changes sign, that's a point of inflection. My darn head got in the way again. So you have points of inflection at 0 and 3/2, because at 0, it changes from positive to negative, f double prime of x, and at 3/2, it changes from negative to positive, f double prime of x. So there's a lot of definitions going on. You want to work through these. You want to start making sense of them, differentiating between different words. And the more we do it, the easier it will be. All right? Good luck.